The James Webb Space Telescope, JWST, has just observed artificial light on the planet Proxima b. JWST's MIRI instrument is capable of detecting large artificial light sources on distant planets. This marks the first real evidence of a technosignature of potentially intelligent life forms on another planet. MIRI is a high-resolution infrared instrument extremely sensitive to infrared radiation, capable of detecting distant metropolitan cities and industrial facilities across the universe. MIRI's capabilities extend not only to our neighboring system Proxima Centauri, it can detect artificial light sources and potential alien cities throughout the known universe. It sounds fantastic what we can do with our new super telescopes. On Earth or from near-Earth space, we can now easily detect large settlements within the known universe. We have already achieved a masterpiece with the MIRI spectrometer at the JWST, and there is even more to come. Another megatelescope will be launched in Chile in 2028, the Extremely Large Telescope, ELT. With a 39 main mirror, this telescope will look deeper and sharper into space than ever before. We need these technical innovations because our thirst for knowledge of the universe is far from quenched. We are only at the beginning of exploring distant worlds, and we need instruments like the JWST and the ELT to examine exoplanets for traces of life. In addition to the ability to detect artificial light emanating from gigantic cities in space or extraterrestrial airfields, we will soon be using a new secret weapon with the LIR system. We will be able to detect traces of vegetation on distant planets. The development will go on in our search for other species in space. We will use more and better instruments and tools until we have found and made contact with other life forms. The first artificial light source on Proxima b. Scientists have long dreamed of this. For the first time, they are using a telescope to look so precisely into our neighboring star system that places of life become visible to us. An artificial light source on the planet Proxima b reveals the presence of technology and therefore also of some form of advanced life. It sounds crazy, but the JWST could even analyze our own activities on Earth based on our light signatures. The best telescopes of all time would easily capture the lights of major cities such as New York, Rio de Janeiro, or Beijing. With its fine sensors, it can filter out the artificial light traces of airports, large industrial plants, or even space stations from the natural light emissions of the Earth. The same is happening on Proxima b for the first time. We will have precise analyses in our hands of where life is located, how much artificial light it produces, and how mechanized the species is likely to be. We have thus made a quantum leap in our search for life in space, and one day we will certainly have the technical means to communicate with other civilizations. If we wanted to send messages to Proxima b, they would take more than 4 years to travel one way by normal means. We would have to wait another 4 years for a reply to come back. All hopes are currently pinned on the development of the first quantum computers. Quantum communication knows neither a fixed place nor a fixed time. Once we have cracked this fantastic technology, we will develop quantum means of communication and communicate with distant civilizations as if in real time. Does that sound like pure utopia to you? Then hold on tight because utopias often become truths very quickly. Simulation of the surface of Proxima b. It was 2016 and a long way from the now very real era of James Webb when scientists dreamed of exploring alien worlds. Back then, a groundbreaking simulation predicted how the James Webb Space Telescope would study the surface of the exoplanet Proxima b in an unknown future. These simulations aimed to analyze the planet's atmospheric and thermal properties. By 2016, researchers were already dreaming of finding out whether Proxima b had an atmosphere that was potentially hospitable to life. What was utopia less than 10 years ago is now reality. At that time, simulations of Proxima b's unique orbit already showed that the highly interesting exoplanet lies within the habitable zone of its parent star Proxima Centauri. The JWST will carry out regular and comprehensive observations of the day and night sides of Proxima b. This planet orbits its star in a bound manner, just as our moon orbits us. Proxima b always has the same side facing its star, and one side is always in shadow. Reconstructions have shown that there must be extreme temperature differences between the day and night sides of Proxima b. Unless the planet has an atmosphere that redistributes heat, without an atmosphere, the day side would be blazing hot and the night side icy cold. The presence of an atmosphere, on the other hand, would allow heat to be distributed more evenly. This is exactly what we can now find out thanks to the JWST. The 2016 simulations showed even more. There could be a temperate strip in the border areas between the day and night sides. It sounds strange to imagine that civilizations exist on a planet that is half light and half dark, and that these beings settle on a strip that is perhaps several thousand km wide around the globe. But it is possible. We need to keep opening our horizons and possibilities in the search for other life forms in space. To be really sure, we need real analysis. In 2016, the exact analyses of the chemical composition of the atmosphere of Proxima b were still a dream. Today, the JWST proves its ingenuity every day and shows us exact analysis profiles for worlds that are sometimes hundreds or even thousands of light-years away. The JWST can recognize signatures of water, carbon dioxide, and methane and has already made a find. The last comprehensive profile was obtained from the exoplanet K218b, where the JWST found evidence of 4 biomarkers in the atmosphere. The more such biosignatures are measured around a planet, the more likely it is that life could exist there. Particularly exciting is the potential discovery of ozone, which is considered a strong indicator of biological activity because it is predominantly produced by biological processes in our atmosphere. K218b could therefore be an inhabited world. However, we have not yet found any traces of artificial light there. This planet could be a pure water world, but that does not mean that it is uninhabited. We have to take into account that there is intelligent life in the water, possibly even cities, and we have to consider that not all developed species have artificial light. We haven't had the light bulb for that long, and yet humans were already intelligent and to a certain extent mechanized in ancient times. The JWST detects plant growth on Proxima b. The James Webb Space Telescope, or JWST, is primarily designed to observe the universe in the infrared range and carry out detailed spectral analyses of distant celestial bodies. What the JWST has not yet proven is its ability to detect plant growth on exoplanets, but it does have the potential to do this. In our search for life in space, we must not only rely on technosignatures and the emissions of highly advanced species. We must also look for planets that may only have plants, animals, or other simpler life forms. The JWST can provide indirect evidence of plant growth by analyzing atmospheric constituents and reflected light spectra. Scientists call this technique vegetation red edge, VRE. These are spectral signatures created by the reflective properties of plants in the near-infrared range. When light passes through the atmosphere of an exoplanet and is reflected by the surface, specific patterns in the reflected light could indicate the presence of chlorophyll or other photosynthetic pigments. The detection of such signatures is still very challenging. The detection of VRE requires extremely precise measurement and high resolution, which can be affected by the exoplanet's atmospheric disturbances and the signal-to-noise ratio. Although the JWST is designed for such measurements, we are now beginning to utilize these capabilities, and researchers are certainly getting better at finding and detecting traces of life in space. We are living in exciting times because the JWST has started a revolution in space exploration, and this development continues. Direct detection of plant growth or biological activity will require future telescopes and missions specifically designed to search for biosignatures. One example is the planned LUVOIR telescope, Large UV/Optical/IR Surveyor, which aims, among other things, to examine the atmospheric properties of exoplanets with even greater precision and to detect potential biosignatures such as the oxygen spectral lines. LUVOIR will be able to isolate and analyze the light from exoplanets even better than the JWST. It will be able to cover a larger number of wavelength ranges, and thus perform more detailed spectral analyses necessary to detect plant or biological activity. Of course, vegetation red edge measurements will also be able to detect possible plant growth on Proxima b and vegetation there. What did the extremely large telescope find on Proxima b? Perhaps you are now wondering how the extremely large telescope could have examined the planet Proxima b if it is currently still being built in the Atacama Desert in Chile. The answer to this question is quite simple. Here too, researchers have created a simulation to show long before the launch how the ELT will scan the sky with its impressive 39M primary mirror. The ELT will be the largest optical and near-infrared telescope in the world, and it will finally go into operation in 2028. The ELT has been specifically designed to analyze the atmospheric and surface properties of exoplanets. With its high resolution and light sensitivity, the ELT can detect extremely faint signals from distant planets, similar to the JWST. By using adaptive optics, this new telescope can also correct atmospheric distortions and thus provide even sharper images and more precise data for Proxima b. This means that the ELT will be able to carry out detailed spectral analyses that will show us the composition of the atmosphere and how high the proportions of water and other biomarkers such as carbon dioxide or methane may be. In addition, the ELT can also use direct imaging techniques to search for possible signs of artificial light or conspicuous surface structures that indicate life or even advanced civilizations. The difference to the JWST lies in 2 points. While the JWST is primarily focused on infrared astronomy and is located deep in space for this purpose, the ELT is a ground-based telescope with a much larger aperture, which gives it higher resolution in the optical and near-infrared range. The JWST is ideal for observing deep infrared sources and exploring the early days of the universe. The ELT, on the other hand, has a broad spectrum and will take us a step further in exoplanet research than the JWST. The aforementioned LUVOIR telescope will be placed in space and will only detect exoplanets to look for biosignatures such as the vegetation red edge. Another important telescope currently under development is the Habitable Exoplanet Imaging Mission, HABEX, which will take the first direct images of Earth-like exoplanets and analyze their atmospheres. The Habitable Exoplanet Imaging Mission, HABEX, is a future space telescope designed to directly image Earth-like exoplanets and study their atmospheres in detail. Scheduled for launch in the 2030s, HABEX aims to revolutionize our understanding of potentially habitable worlds beyond our solar system. Unlike the JWST and the ELT, which focus on spectral analysis and detection of biosignatures, HABEX will use advanced optics to capture images of exoplanets. This capability will allow scientists to study planetary features such as continents, oceans, and cloud formations, providing insights into their potential habitability. One of the key objectives of HABEX is to detect and characterize exoplanets that resemble Earth in size, composition, and orbit around their stars. By directly imaging these exoplanets, HABEX will be able to analyze their atmospheres for gases that could indicate the presence of life, such as oxygen, methane, and water vapor. These gases, if found in abundance and in the right proportions, could provide strong evidence for biological activity on these distant worlds. HABEX will also study the evolution of planetary systems by observing young stars and their surrounding protoplanetary disks. These disks contain the material from which planets form and evolve over time. By studying the composition and dynamics of these disks, HABEX will shed light on the processes that lead to the formation of planetary systems like our own solar system. Another important aspect of HABEX's mission is to investigate the prevalence of exomoons, natural satellites orbiting planets outside our solar system. Exomoons could potentially harbor environments suitable for life, similar to Jupiter's moon Europa or Saturn's moon Enceladus in our own solar system. Detecting exomoons and studying their properties will contribute to our understanding of how common habitable environments may be in the universe. In addition to its scientific objectives, HABEX will also push the boundaries of space telescope technology. It will incorporate advanced imaging systems, including coronagraphs and starshades, to block out the glare of parent stars and directly image faint exoplanets nearby. These technologies are crucial for observing Earth-like exoplanets, which are billions of times dimmer than their host stars. The development of HABEX involves collaboration among NASA, international space agencies, and the scientific community. Planning and designing such a complex mission require interdisciplinary expertise in astronomy, astrophysics, optics, and engineering. The telescope's instruments must be highly sensitive to detect faint signals from distant exoplanets while maintaining precision and accuracy in their measurements. Moreover, HABEX will contribute to our broader understanding of planetary science and astrobiology. By studying a diverse range of exoplanets, from hot Jupiters to potentially habitable rocky worlds, scientists can explore the full spectrum of planetary diversity in the universe. Each new discovery adds to our knowledge of planetary formation, evolution, and potential habitability conditions beyond Earth. Looking ahead, The launch and operation of HABEX will mark a significant milestone in the search for life beyond our solar system. It represents a leap forward in our ability to study exoplanets in detail and investigate their potential to harbor life. The data and discoveries from HABEX will inspire new generations of scientists and deepen our appreciation of the vast diversity of worlds that exist beyond our cosmic neighborhood. In conclusion, the Habitable Exoplanet Imaging Mission, HABEX, holds immense promise for revolutionizing our understanding of exoplanetary systems and potentially finding habitable environments beyond Earth. By directly imaging Earth-like exoplanets and studying their atmospheres, HABEX aims to detect biosignatures and provide insights into the prevalence of life in the universe. Through advanced optics and imaging technologies, HABEX will push the boundaries of space telescope capabilities and pave the way for future discoveries in exoplanet research.